Good afternoon. I am Subramandal from University of Bardwan. I am going to talk about our present work on the dynamics of cosmological phase transition of Bose Einstein condensate and dark matter in Tsalli's cosmological framework. So we all know that standard cosmology explains many things, but it has some tensions like missing satellite problems, core cast problem, and age problems. So Bose-Einstein condensate, what it does, that it introduces some quantum pressure, uh, and it can fix that small scale issues, and that Tsalli's entropy, this generalizes thermodynamics for gravity, for long range interactions, and from this we can explain the age of the universe and the acceleration of the universe without considering dark energy. So our goal is to consider both of the frameworks and merging it and study the evolution of the dark matter from its normal to Bose-Einstein condensate state. So start with the Boltzmann-Gibbs entropy. We know that it is good for short-range interactions and independent systems, but it fails for long-range interactions like gravity. So here some consequences are, we get divergent partition functions, and that entropy energy relations inconsistencies for gravity. So we require some other theory, and for that we consider that Tsalli's cosmology. Thus Tsalli's cosmology emerges from Tsalli's entropy. It is a non-additive in nature, and it can explain gravity, and from this we can explain the acceleration of the universe without considering dark energy. We consider dark matter as boson particles. So it may possible that whenever that universe cools down to certain temperature, it can form Bose-Einstein condensate, and it can be governed by Gross-Pitofsky-Poisson's equations. And before that condensation, it acts like a normal dark matter and follows linear equation of state. And after that, that equation of state is like it quadratically depends on density. So when it forms BEC condensate, we consider that is a first order phase transition, because some of the mean field theories suggested that it is a first order phase transition, and for that we keep that pressure and temperature fixed during the first order phase transition and calculate that temperature, critical redshift, scale factor, and some other quantities. So for a typical value of mass of dark matter 0.55 eV and scattering length of order 10 to the power minus 10 centimeter, that critical redshift comes 1200, and the time corresponding to it is 10 to the power 11 seconds. So these are the typical values. We don't have that data analysis. So we keep some constant that that it cannot go beyond 6 eV, because beyond 6 less than 6 eV can form BEC condensate for any temperature in cosmological framework. So we define a quantity condensate fraction and shows how it evolves with time, and from that we can find that the total time duration to form a condensate, and it is about 4.3 into 10 to the 12 second for a typical value of the Tsalli's parameter 0.35. And we calculate the deceleration parameter. We can see that deceleration parameter is solely dependent on the Tsalli's parameter beta, and for beta less than half, we can see that q takes the negative value, so we can explain the accelerated universe without considering any dark energy. So these are some plots that how that condensate factor grows, and that grows with time for different Tsalli's parameter value, and that distillation parameter varies with beta, and other two graphs are that Hubble parameter, how it changes with time for different beta values during condensation and after condensation. So now we can fix that age problem also. We know that in matter-dominated universe, that age of the universe is predicted is below 9 gigayear. But if we consider as Tsalli's cosmology, it can alleviate the time nearly 1.65 times. So it can, it can solve that age problem of the universe, and there is no discrepancy remains, and this we can do without considering dark energy. So this has been published in this article, so you can see. Thank you.
Thank you, Subhra.